All right. Okay. So welcome back to lecture three of the course. So this is where we will finish up the discussion around descriptive statistics, and then from in the next session we'll move on and start talking about probability theory and how it relates to inferential statistics and move on with the course. Right. So just as a quick recap of as to what we are doing here, the idea is fairly straightforward. Right. With statistics, all you're doing is working with data, using the data to gain some useful insights about the state of the world. And in order to do that, we need a few mathematical techniques to accomplish that end, right? So in the first order of business, what we'd like to do is to look at the raw data that we've collected and begin to sort through it and begin to describe it and get a basic understanding of what the data set looks like, right? At this point, we are not yet really talking about using the data to inform any decisions or come up with any insights. All we're trying to do is just understand the data. Right? So in the last session, that's what we did. We talked about how do we organize the raw data in the form of frequency distributions. How do we summarize what we are seeing in the raw data? We saw the whole range of different kinds of visualizations that we can use to summarize the raw data. So in this session, then we'll talk about measures of central tendency. So we'll talk about some analytical measures of how do we summarize the data. We're still in the realm of looking at raw data and using some kind of techniques in order to describe the data, to summarize the data set itself. But this is where we begin to talk about more analytical measures. And the first measure that we'll talk about, first set of measures I will talk about is what we call measures of central tendency, right? So in this section, we're going to try to figure out how to find the mean, the median, and the mode. What do we even mean by measures of central tendency? And then we'll talk about two special cases. One is when you have to find the weighted mean of a data set, and one in a case where you just have a frequency distribution. How do you calculate a mean when all you have available is just a frequency distribution? And then we'll talk a little bit about different kinds of shapes of these distributions. All right. All right. So with the measure of central tendency, what we're trying to do is fairly straightforward. We have a raw data set. We're trying to find one number which describes the typical entry in the data set, a value that represents a typical or central entry of that data set. So if I asked you, just give me one number which gives me just an indication of what a typical value in the data set looks like, that's what we mean by measure of central tendency. And the most commonly used measures, there's three commonly used measures for central tendency, what we call the mean, what we call the median, and the mode. Okay. So we'll take each of these in turn. The mean is something that I'm guessing everyone is already familiar with. The mean is what we also call the average, where we essentially sum up all the entries and divide by n, right? So So here we use the sigma notation. I'm guessing by now you're familiar with the sigma notation, but just in case, when we write the sigma, all it means is sum, right? So we've seen this notation in the previous lecture also. So all this is saying is that take every single entry in the data set, add them all up and divide by n, which is the total number of entries in the data set, and that tells us the mean, right? So in a certain sense, uh, you, if you want to really understand what is happening here, we are weighting each entry in the data set by the same amount, right? So we are coming up with an aggregate measure for a typical value in the data set by giving equal weightage to every single entry in the data set, right? So here's an example and you'll see what I mean. So suppose you collect a sample, right, of round trip flights from Chicago to Cancun, and these are the prices, right? So there's a wide variation in the prices, right? There's prices, tickets which are fairly cheap, tickets which are very expensive. There's a lot of variation in the prices, but the question we're trying to ask is not how much variation there is in the prices. All we want to know is that if I want to take a trip to Cancun, what is on average, what is the typical amount I should be looking to spend on plane tickets, right? So one answer to that is to basically find the average, and the average essentially takes each of these values, 1, 2, 3, 4, 5, 6, 7. There's 7 values, adds up all the 7 values. So sigma x is essentially saying sum up all the values in the data set, and then you divide by the total number of entries in the data set, which is 7. And so the average is about $527.90, right? So the mean price of the flights on the sector is about $527.90. So on average, if I want to take a trip, uh, an average, if you want a slightly more nuanced interpretation of what the average is saying, the average is saying that, okay, if I take multiple trips between Chicago and Cancun, sometimes I'll end up spending a lot of money. Sometimes I'll end up spending, I might get lucky and get cheap tickets. But on average, if I keep doing this over and over again, on a typical trip that I make on this sector, I would end up spending about $527.90, right? So that's what the average is telling us. All right. So that's the first measure of central tendency that we want to think about, which is the average, right? So when we divide by n here, what we are saying is that each of these entries, because if you think about this 3695, it's the sum of these 7 numbers. So if I'm dividing by 7, it tells me that each of these entries in the data set that I have is getting weighted by 1 over 7, right? So about a seventh of the weight of the measure that I call the mean is given over to each of these entries. So that's what a mean, that's the reason why we can think of mean as a measure of central tendency, because I'm taking into account every single entry in the data set, but I'm ascribing the same weight to every single entry in the data set, and I'm coming up with a measure which tells me what the typical value in the data set looks like, right? So the second measure of central tendency that we like to talk about is the median. And the median is a very intuitive measure of central tendency. And the median, with the median, when I ask you what is the typical value in the data set, you can think of it and say, okay, somewhere in the middle, whatever is in the middle of that data set, the entries which are in the middle of the data set must be typical values, because they're neither extreme, they're not neither at the start, they're not very small, nor are they very large. They're somewhere in the middle, so that should represent typicality, and that's basically the idea behind the median, right? So the median is essentially finding the middle of the data set when the data is ordered. So obviously it needs to be ordered. It needs to go from largest to smallest to largest. It can't be in some haphazard, right? The middle only makes sense if the things that are you're looking for the middle in are ordered, right? The data set itself is ordered. And so it depends on whether the data set, when we calculate the median, there's a small nuance, and I'll show you the nuance with an example. But if the data set has an odd number of entries, median is always the middle data entry. And if it has an even number of entries, median is the average of the middle 2 entries. So I'll show you what that means in just a second. Okay. So same example that we had, right? So we calculated these prices. So we went out and observed these prices to take these round trips from Chicago to Cancun. And then we have these 1, 2, 3, 4, 5, 6, 7 different prices. Okay. We already figured out how to calculate the mean. Well, how would you go about calculating the median? The first thing to do before you calculate the median is to put this in some kind of an order, right? In ascending order. So first we order the data. So, in ascending order, the smallest entry comes first, the largest entry is in last, and we've essentially sorted the data, right? So now that we have we've sorted the data, the median is the middle of the data set, right? So the median is where this is an odd number of entries, and this is the middle entry. So if I have 1, 2, 3, 7 entries, then the fourth entry is the middle entry. Why is the fourth entry the middle entry? Because now if I break the data set here, there's 3 entries to its left, 3 entries to its right, which means that it breaks the data set into 2 equal halves, and this is the middle entry, right? So if you have an odd number of um, entries, then the median is going to be the middle entry, and the middle entry is generally going to be n plus 1 over 2, right? So n plus 1 over 2, right? So if I have 7 entries, then this is n is 7, 7 plus 1 is 8, 8 over 2 is 4. So I know that the median is at the fourth entry, right? So that's fairly obvious. So if I have an odd number of data entries, then the middle entry, I can just find it First, I order the data, then I go look for the middle entry, which breaks the data set into two equal halves, and that becomes the median for that data set. Okay. So what happens if I have an even number of entries? Okay. All right. So suppose this price for flight price at $432 is no longer available, and I have only 6 data entries. How do I find the median here? You can see what the problem is. First, you anyway go ahead and order the data. That's fine. Now the question becomes, where do I break that data set? Okay. So if I take this to be the median, right, 397 to be the median, I have 2 entries to its left, but 3 entries to its right. That's not the middle of the data set, strictly speaking. But if I go to the next entry, which is 427, now I have a different problem. I have now 3 entries to its left, but 2 entries to its right. So it's not the middle of the data set either. So then the question becomes, okay, how do I find the, if I have an even number of entries, how do I find the median? I look at the middle 2 entries, which is 397 and 427, and average them out. I say some midpoint between these 2 entries will act as the median entry for the data set. Right. So the median in this case is the average of the middle 2 entries, which is 397 plus 427 over 2, or 402. Okay. So that's the key thing to note when we are dealing with the median. The first thing with the median is that it's representing the middle of the data set, the 50% entry, the midpoint of the data set. The second thing is that it only works once you order the data, because to find the middle you need to know where the start is and where the end is for the middle to be defined. So you need to order the data set to begin with, and depending on whether you have an even number of entries or an odd number of entries in the data set, the calculations around the median change. If it's an odd number of entries, it's very straightforward. The middle entry is the median. And if there's an even number of entries, then you look for the middle 2 entries and average them out. Right? That tells you what the median should be. All right. So the third measure of central tendency that we like to talk about is the mode, right? So with the mode, again, the idea is fairly intuitive. So if I ask you, okay, what do you think the typical entry in the data set should be? And straight away you can think of, okay, the entry which appears with the highest frequency, the entry which appears the most often in the data set, that should represent the typical entry in the data set. And that's basically the idea behind calculating the mode. The mode is essentially the entry which occurs with the greatest frequency. And if no entry is repeated, then the data set has no mode, obviously. So if there is no entry in the data set which doesn't show up repeatedly, at least twice, not more, then there is no mode to the data set. If there are more than one entry which are repeated the same number of times with the same greatest frequency, then each entry is a mode. So then you have what we call a bimodal data set, and you might have many data set which is trimodal, and so on and so forth. So if there are many entries with the same highest frequency, then they are all act as modes in the data set. Okay. So for instance, in our example, if I had to think about the mode, I want to find the entry which repeats itself the most often. In this case, there's only one entry which repeats itself, which is 397. So in this case, 397 is the only entry which repeats itself, and that is the mode for the data set. Okay. So here's a second example. So at a political debate, a sample of audience members were polled, and they were asked to name what party they belong to. Okay. Now, 34 of the people, 34 people, or 34 members of the people who were polled said they were Democrats, 56 said they were Republicans, 21 said other, and 9 didn't respond. Okay. So if I had to say what is the typical person in that room look like, and you would say, okay, there's obviously a lot more Republicans um, in the room relative to any other sort. So if I think about the mode of the data set, the mode is Republican, right? The typical entry I would come up with is that it's Republican. But straight away, you can see what the problem could be with using mode as a measure, right? In this case, there's not much of a problem, because it is the single largest frequency, and the next largest frequency of Democrat is relatively much smaller than this, so it's okay. This seems to be representing the typical value. But suppose instead of having 34 Democrats here, suppose you had 55 Democrats. Okay? So instead of this being 34, suppose there were 55 Democrats. Now, the answer wouldn't still change, right? If I asked you what is the typical entry and you relied on the mode, then you would say, yeah, the typical person in the data in the room is a Republican. But in fact, that might not be true because there is almost as many Democrats as there are Republicans in this room, right? And straight away, when the frequencies between different classes are very close to each other, like in this case, where it is 55 and 56, the mode might give us a false sense of what the central tendency looks like, what the typical measure in the data set looks like, right? So in generally speaking, we never end up using the mode as a dominant way of thinking about central tendency, because it's not a particularly informative way. It's a very crude way of thinking about typical values in the data set. Okay? So the three measures, all three measures that we discussed here, the mean, the median, and the mode, all three of them are measures of central tendency, or they're telling us what a typical entry of the data set looks like. Okay. Now, each of them has their own advantages and disadvantages. The mode we've already discussed what the disadvantages. If there's two entries with very close where the frequencies are very close, the mode might not really give us an accurate description of what typical looks like in the data set. So it's usually going to be a contest between whether we use the mean or the median as the measure of central tendency. Okay. And the question is generally resolved as to whether we use the mean or the median by looking at whether we have outliers in the data set. So the rule of thumb is that if there are outliers in the data set, okay, I will discuss outliers and how it affects the mean. But the rule of thumb is that if there are large outliers in the data set, then the mean is a biased measure of central tendency, and we much rather use the median rather than the mean to measure typical values in the data set. Okay. So the big disadvantage of using the mean is that they're greatly affected by outliers, and I'll show you an example to illustrate this point. All right, so here's an example where we can look at all three measures of central tendency and then decide which is the better measure of central tendency. All right. So we have recorded the ages of all the people in the class, and it turns out, there's a lot of 20-year-olds, 21-year-olds, 22, and there is a large outlier here, a 65-year-old who's just in the class as well. Okay. So we want to know, given that this is a data set that we've collected, we might want to know what the typical value in the data set looks like. So we can go ahead and calculate all three measures, the mean, the median, and the mode. Okay. So how do we calculate the mean? We add up all these entries in the data set. There's 20 entries in the data set. We add them all up, and then we divide by 20, and that tells us the mean is 23.8 years in the data set. Okay. Now, what about the median? Now, if I had to find the median, now look at this. There's 20 entries in the data set. So there's an even number of entries. So there's not going to be a single entry which is a middle entry. So I have to find the middle two entries in the data set and average them. So if I think about this 20 entries, so the middle is going to be between the 10th. So if I go in the order, so it's 1, 2, 3, 4, 5, 6, 7. This is the 8th entry, 9th, 10th, right? This is the 10th entry. So if I can't choose this to be the median, because what happens if I choose this to be the median, then I have 9 entries to its left and 11 entries to its right. So that's not exactly half, right? I can't choose 22, which is the 11th entry, because then I would have 10 entries on this side, but only 9 entries on the other side. So I would choose the midway point between these two to represent the median, and that's what I have here. The median is the average of the middle two entries in the data set, which is 21 plus 22 over 2, which is 21.5 years. Okay. And if I want to know the mode, I want to know the entry which appears with the highest frequency. So in this case, 20 appears with the highest frequency. There's 20, 1, 2, 3, 4, 5, 6. 20 appears 6 times, 21 appears only 4 times, 22 appears 3 times, 23 appears 4 times, 24 appears twice, and 65 appears once. So the mode, which is the entry which occurs with the highest frequency. So in this case, it'll be 20 years. Okay. Now the question is, which of these entries is a better measure of central tendency? So we understand that all three are measuring something about the typical value in the data set. All three are measures of central tendency, but which is preferable? Right? So the mean says it's 23.8 years, the average is 23.8, the median is 21.5, the mode is 20 years. Generally speaking, we don't use the mode as a measure of central tendency because it has this problem that, yeah, there is 1, 2, 3, there's a 6, there's more 20-year-olds in this class than any other kind, but that's not like the distribution is fairly close. Yeah, there's a lot of 20-year-olds, but there's also a lot of 21-year-olds and a lot of 22-year-olds, a lot of 23-year-olds. The frequencies between them are not that different that we can rely on the mode to be a reliable measure of central tendency, right? So even though the mode exists, we don't generally rely on it to be a measure of central tendency. Now, the question is between the mean and the median, which is a better measure of central tendency, and the question comes down to whether there's an outlier or not. Okay. Now, if when there is a large outlier, as it is in this case, 65, it's an outlier because most of the data set is concentrated around this range between 20 to 24. And then there is this random entry, which is in here, which is 65, which opens up this big gap between this entry and the rest of the data set. And so this is how what we call an outlier is where we find entries which are not closely clustered together, but rather very far apart from that data set. Okay? So if there is a large outlier, the mean is going to get pulled in the direction of the outlier, because what we know about the mean is that it takes into account each of those entries, every single entry, and gives them equal weightage. So if there is a large entry on one side or a very small entry on the other side, the mean is going to get biased in that direction, right? So the mean is now getting pulled up to 23.8 years. And that's largely as because of this presence of this outlier here. Okay. So when we talk about measures of central tendency, in this case, because there's a large outlier present, the mean doesn't give us such a great measure of central tendency. So we end up relying on the median as the best measure of central tendency because it is, even though it's taking into account all the entries in the data set, it's not biased, it's not influenced by the magnitude of outliers, it's not influenced by the size of the outliers, and not heavily get it doesn't get pulled in that direction, even though it's taking into account all the entries in the data set. Okay? So when there is an outlier present, then the mean becomes it's a biased measure of central tendency, and then we rely on the median. So the mode is never usually in the contention, so you can straight away not worry about the mode for the most part. Very rarely do we think about using the mode as the measure of central tendency in very specific cases. But for the most part, it's going to be between the mean and the median, and the question comes down to whether you have an outlier problem or not. If there's a large outlier, use the median. If there is not an outlier, then use the mean. Generally speaking, the mean is the most common measure that we use in statistics, but that's one thing to keep in mind. Okay. All right. There is a couple of special cases of calculating the mean that I won't quickly go over. This notion of a weighted mean, and we'll talk about when we have only a frequency distribution. Okay. So when we calculate the simple mean, right? So the difference between a simple mean, the usual average, and a weighted mean is that in a simple mean, every category carries the same weight, right? If there's 10 numbers, each of those numbers counts for 1/10 of the weight in the measure, right? With the weighted mean, we might want to change how much weightage we give to each of those entries. And this is best understood from an example, and I hope this makes things clear fairly quickly. So here's an example where you might want to find a mean, find the average when not every single category carries the same weight. So the difference between the simple mean and weighted mean comes down to what weights we are assigned. So for instance, suppose you're taking a class, this is a typical example where there's different categories on which you're graded, and each of them are not weighted the same way, right? So 50% of your grade depends on your test mean, 15% from your midterm, 20% from your final exam, 10% from your computer lab work, and 5% from your homework. So what we have here is the different weights that are assigned to each of these categories, right? So we had to calculate the weighted mean. So these are the weighting schemes. So the test mean will account for 50% or 0.5. That's the proportion, that's the fraction. So midterm accounts for 15%, so that's 0.15. The final exam accounts for 20% or 0.20. The computer lab for 10%, and the homework for 5%. And these are your scores on each of those. So where are these numbers coming from? So your scores are was 86 was your test mean, 96 was your midterm score, 82 was your final exam, 98 on your computer lab, and 100 on your homework, right? So if I had to just take the average of these numbers, if I took the average of each of these numbers, I would add up these five numbers and divide by 5, right? That's a simple average. But in this case, that's not what I want to do, because I don't want each of these categories is not weighted the exact same way. Each of these categories is assigned a different weight. So of the total score that I want to calculate, 50% of it depends on the score on the test mean. So I multiply that, so that 50% portion of the weighting of the final score is on the test mean. So that's 0.5 times 86. So out of that 50%, you got a 43%, which is what the test means proportion represents. Similarly, the midterm accounts for 15% of the grade. So out of those 15 points, a 96 on 100 is equal to 14.4 on 15. So that's what it means to multiply this by 96 times 0.15. Okay. And the final exam counts for 20%, and so on and so forth, right? So here is a case where the weights that we are assigning to each of these categories is different. So sometimes when we don't want the equal weighted, generally speaking, when you calculate the average, the each of those entries is given the equal weight. But if we want to reject the weights that we assign to different categories, then we might have to use a system like this, where we first come up with all the weights that we are going to use for each of these different categories, and then we can calculate the mean. So the weighted average here is 88.6, right? So if you run the same example, if you just calculated these simple average of these five numbers, which is to just add these five numbers and divide by 5, you'll find that that's like 92.4, right? But that's just if in a simple average, if I have five different categories, and if I calculate the simple average, what I'm saying is that each of those categories counts for 20% of the final grade, because 1 over 5, because when I divide by 1 over 5, what I'm doing is that I'm giving each of those weight of 0.2 or 20%. So that's the difference between when we have a simple mean where each category has the same weight of 20%, 5 categories, each of them is worth 20%, versus a weighted mean where each of these categories is weighted different. Right? All right. The next example, that the next special case I want to say, which we want to take into account here, is the case when we have a frequency distribution, right? Suppose we have no way of knowing the underlying data set, and what we are just given is the frequency distribution. So again, let's take a look at an example. So let's take a look at an example just to understand this. So suppose I've just given a frequency distribution like this. So I have all these different classes. We've seen what a frequency distribution is from the last time. So we have all these different bins into which we're going to solve the data into, and the frequency. Okay. So here's a case where I don't know what the underlying data set looks like, right? I don't know what all the numbers in the data set themselves are. All I know is that there are 6 numbers in this data set between 7 and 18. Right? And there's 13 numbers in this data set between 31 and 42. That's all I know, right? I don't know what the numbers are. Are they all 13, right? Like, or are all these 13 numbers that are between 31 and 42 just 31s? Could be. Are they all only 35s? Could be, but I have no way of knowing that. All I have is this information that has been given to me, that the classes, or these are the different classes the data set is sorted into, and this is the frequency of each of these classes. There's a number of entries in each of those classes. And suppose based on just this information, if I wanted to calculate what the typical entry or what the average is in the data set, I can still do that. And the crucial insight is to say, yeah, I don't know what the exact numbers are, right? I know there's 6 numbers between 7 and 18, but I don't know what those numbers are. So what I'll do is that I'll use the midpoint of that class as a stand-in for the entry for the class, right? So I'll use just the midpoints of each of those classes to stand in as the representative entry for that class. So 7 to 18, the midpoint is 18 plus 7 over 2, which is 12.5. Right? So I would treat it as if I have 6 numbers of 12.5 in each of those in that class, right? So that's 12.5 times 6, which is 75. Hmm? So again, in the class 19 to 30, I don't know, I know that there's 10 numbers in that class. There's 10 numbers between 19 and 30 in the data set. I don't know what those numbers are. So instead, I'll use the midpoint of the class as the approximation or the representative for the entirety of the class. And the midpoint of that class is 19 plus 30 over 2, which is 24.5. So I'll treat it as if there's 10 24.5s in the data set. So this is basically adding up 12.56 times, which is 75, adding up 24.5 10 times, which is 245, and so on and so forth, right? So here I have the sum of all of that, and then I divide by the total number of entries in the data set, which is 50, and I get the average, right? So when I have just a frequency distribution where I just know the different classes into which the data has been sorted and the frequencies of each of those classes, then I can still come up with an approximation. So this is by necessity an approximation. This is not an exact number, but this is an approximate number of what the mean would look like, given that we are assuming that the midpoint is the representative of each of these classes. Okay. So that's the second special case I want you to keep in mind. One is the case where we might want to calculate the average where the weights are not the same. So that's the case where you might want to do a weighted average calculation. And the second thing is that when you're just given a frequency distribution, you have no way of knowing what the underlying numbers are, then how do you go about calculating the average in that situation? All right. All right. So now the last thing I want to talk about in this section are about the shapes of these distributions. Okay. Now we'll talk about this in more detail as we go along in this course, but here's a quick intro into it. Right? So the first kind of distribution that we generally concern ourselves with is what we call a symmetric distribution. So if I draw a histogram like this, right, there's a histogram, the frequency histogram, and if I connect up these things, this is not a thing, but okay. Anyway, so point of this is that a symmetric distribution is one where if I draw a line through the center of that distribution, it breaks the distribution into two equal halves, right, which look like mirror images, right? So this is what we call as symmetry. So if I try to pass a line through the center of the distribution, then the entire distribution, the shape of this distribution is turns into two equal images which look like mirror images of each other, right? So if that is the case, then I say that the distribution is symmetric. Okay, so visually that's how I know when a distribution is symmetric. But in an analytical sense, if I want to know how a distribution is symmetric, this a distribution said to be symmetric if the mean, the median, and the mode are all the same, right? If the mean, the median, and the mode is all the same, then we say that the distribution is symmetric. So there's a special kind of distribution which is called the uniform distribution. A uniform distribution is where every single entry in the data set has the same frequency, right? So every single entry is repeated the same number of times in the data set, which is to say this is a data set which doesn't have single mode, right? Because every entry is repeated with the same frequency, same highest frequency. So every entry is like an entry of 1 is repeated 20 times, the entry of 3 is repeated 20 times. Every single entry is repeated the same number of times. So there's no mode to the data set, but it's still symmetric in the sense that if I draw a line through the center of this distribution, it breaks into two equal halves. So as long as the mean and the median are equal, then we say that the distribution is symmetric. Okay. So that it's a special kind, uniform distribution is a special kind of a symmetric distribution in the sense where the mean and the median are the same, but the mode is doesn't exist. But generally speaking, when we talk about a symmetric distribution, we are talking about distributions where the mean, the median, and the mode are all the same, right? They're all if I draw a line through the center of the distribution, it breaks the distribution into two equal mirror images. Okay, so straight away you can tell that there would be two special cases here of what we call left skewed and right skewed distributions. When we think about a skewed left distribution, which is also called a negatively skewed distribution, there is more weight in the left tail. So if I think about what the shape looks like, this looks like this. Okay, so the left tail of this distribution is more elongated than the right tail of this distribution, suggesting that there's more entries in the left tail of this distribution than there are in the right tail, right? So we know straight away that the mean is the entry which gets biased because of outliers. So because there is more entries on this left end, there are bigger outliers on the left end of this distribution, the mean gets pulled towards that. Right? So this is a case if where the mean is to the left of the median, right? The mean is to the left of the median because why is that the case? Because there's more outliers in the left tail of this distribution, which means that the mean is pulled towards those outliers and the mean is less than the median, right? So if the mean is less than the median, then we know that the distribution is what we call a negatively skewed distribution or a skewed left distribution. And similarly, we have the other case where the mean gets pulled to the right of the distribution. So if I look at the shape of this distribution, not really great drawing with the thing, but like you can see that there is more entries, more outliers in the right tail of the distribution than there are in the left tail. And this is a case where we have a skewed right distribution, right? So because the mean gets pulled to the right because there's outliers in the right tail, so now the mean is going to be greater than the median. If the mean is greater than the median, then we say that we have a positively skewed or a skewed right distribution, right? So that's basically what I want to do in this section. So we figured out of the first analytical measures in descriptive statistics. So we want to know what is the typical value in the data set, what we call the measures of central tendency. We discussed the three usual measures of central tendency that I use, the mean, the median, and the mode. And depending on the circumstances and the data set, one measure might be preferred over the other. Generally, it's going to be a thing between the mean and the median, and the choosing between the mean and median, which is a better measure of central tendency, basically is determined by whether we have an outlier problem or not. If you have an outlier problem, then the median is preferred. If we don't have an outlier problem, then the mean is preferred. Then we talked about the two special cases where we might want to weight different entries with different weights. So we talked about how to calculate the weight and mean. And then we also talked about how to calculate the mean, approximate the mean, I should say, when we have only information on the frequency distribution, but have no access to the underlying data set. And finally, based on the location of the mean with relationship to the median and the mode, we might come up with different shapes of these distributions. So if the mean, the median, and the mode are all coinciding with each other, then we say that the distribution is symmetric. Then if the mean is less than the median, then we say that the distribution is left skewed. And if the mean is greater than the median, then we say that the distribution is right skewed. Okay. All right. So that concludes this section on measures of central tendency. Now we'll quickly move on and talk about measures of variation. Okay. Okay, now we'll turn to talking about measures of variation, right? So in this session, the first thing we talked about is what does a typical entry in the data set look like and how do we measure it? Now, the second question that we might want to consider is what happens with measures of variation, right? How much variation there is in the data set, how much spread there is in the data set. Are all the entries in the data set very clustered together or are they spread far apart, right? So now straight away we are beginning to understand the basic characteristics, the basic description of the data set, because now we have a visual representation of it, a sorting mechanism for how to sort through the data. Now we have a measure of the typical entry in the data set. We know what a typical entry looks like. And now the fourth order of business is to consider how much variation there is in the data set, how much spread there is in the data set. So we'll talk about how to find the range of a data set, how to find the variance and standard deviation in both the population and the sample data set. There's a small difference there that you need to be aware of as to what the formula, the difference in the formula is between a population data set and a sample data set, and how we find the variance and standard deviation there. I will talk about a couple of key ideas called the empirical rule and Chebyshev's theorem, and a couple of special cases, right? How to approximate the sample standard deviation when we have group data, which is to say a frequency distribution, and then what the coefficient of variation has to say about all of these things, right? All right, so before we get into all of that, let's begin with a simple idea. Now, if I asked you intuitively, okay, come up with a measure of how much variation there is in the data set. And the most intuitive measure seems to say, okay, let me look at where the data set begins, what is the minimum entry in the data set, and where the data set ends, which what is the maximum entry in the data set. So that difference tells me how far apart the start of the data set and the end of the data set is. And that tells me how much spread there is in the data set. And that's what we call the range. So the range is essentially the difference between the max data entry minus the min data entry. So for instance, if I have this data set here, uh, the starting salaries for each of these 10 graduates is shown. And if I want to find the range of this data set, I want to find the min entry and the max entry. So maybe first I order the data set from in ascending order from smallest to largest. So the smallest entry is 37, the largest entry is 47. So the range of this data set could be 47 minus 37, which is 10. Okay, or $10,000 because they're all represented in thousands of dollars. So that's the first measure that we can think of as to what the uh, measure of dispersion in the data set is, measure of variation in the data set. Okay. So that's not bad for the first attempt to think about a measure of variation. Now the question is, can we come up with a more nuanced measure of how do we measure variation in the data set? And the idea that we come up is what we call the variance and the standard deviation. Okay. So the basic intuition of coming up with these measures is fairly straightforward. So when we are measuring the variance or the standard deviation, we are concerned with how the rest of the data is distributed around the typical entry, right? So when we talk about the deviation, we're talking about the difference between a data entry and the mean of the data set. If the mean is representing the typical entry of the data set, we want to know whether the other entries in the data set are close to the typical entry, which means that this deviation will be small, or are they large, which means that the deviation will be much bigger, right? So if the deviation is much bigger, that gives us an indication that there is more variation in the data set relative to the typical entry. And uh, if the measure of variation is small, then it gives us an indication that there's not as much deviation. They're all closely clustered together. All the entries in the data set are clustered around the mean. Okay. One key thing to note here is the difference in notation. Mu here, the Greek letter mu here refers to the population mean. So if we have a population data set, then we use the letter mu to represent the population mean. If we have a sample data set, then we use the thing x bar to represent the sample mean. Just make sure that this is a notation is not just merely notation. You need to know that there's a big difference there between whether you're dealing with a population data set and a sample data set. Okay. So let's think about how do we calculate the deviations and the variance and standard deviation. Okay. So now we have the same data set. Corporation hired 10 graduates. So these are the salaries, the starting salaries of those 10 graduates. Before we do anything else, we want to know whether this is a population data set or a sample data set. Okay. So this has data on all 10 graduates that the corporation has hired. So we have data on every single one of them. So this is a population data set. Okay. So the first thing we need to do before we can calculate a measure of variation, where before we can calculate the variance or the standard deviation, is to know where the typical entry in the data set is. So the first thing we do is to calculate the mean of the data set. How do we calculate the mean? We add up all the entries in the data set and divide by the total number of entries there are. So if I add up all these 10 numbers together, that's 415 over 10. So the typical entry in the data set is 441.5. Now I want to know how the rest of these entries, how the entire data set is located, how far or close they are to the typical entry. And there, that's where I take the deviations. So if I look at the first entry, which is 41, the deviation of this entry from the mean is negative 0.5. The negative suggests that it's lower than the mean, is to the left of the mean, and the 0.5 tells me that that's the magnitude, that's the distance away from the mean it is. So straight away, so 38 here, again, the deviation from the mean is 38 minus 41.5. So the mean is 41.5. Where do I get this from? We just calculated that the mean is 41.5. So each of these entries, the deviation from the means are calculated. Okay. So this seems reasonable. So if I know how far each entry is from the mean, and if I can add them all up, then maybe that gives me a measure of variation. And so far that's a reasonable intuition. But the problem we run into is that if I sum the column of deviations up, that'll always sum to zero. Just by the way the mean is constructed, this is always going to be true, right? If I take the column of these deviations and sum them up, it is always going to sum to zero. And now I have a problem. So far, my thinking is right. First, I figure out what the typical entry is. Then I want to figure out how far each of the entries in the data set deviate from that typical entry. And I was like, okay, so far that's good. But if I aggregate them, if I want a single number which represents all these deviations together, that column, the sum of this column is always summing to zero. Okay. And so the one way we can overcome this is that, it turns out that these negative values and positive values are lining up in such a way that they're always summing to zero. So why don't I just turn them in, all the negative numbers into positive numbers? And the way we turn negative numbers into positive numbers is to square them. So that's the idea. That's where we get this sum of squared deviations from. Okay. So the population variance. So if you have a population data set, this is, yeah. Where the population data set, this is the Greek letter for sigma. Sigma square, which is a population variance, is some of the uh, deviations, some of the square deviations divided by n. Okay, and the population standard deviation is just the square root of that variance. Okay, so the standard deviation is always just the square root of the variance. So in this case, if you're dealing with a population data set, then the population standard deviation, which is represented by this Greek letter sigma, is just the square root of the variance that you calculate. Okay. So here I have a quick little recipe book to follow. When you have a population data set, how do I find the variance and the standard deviation? And the idea is fairly straightforward. First, you find the mean, which is the typical entry in the data set. Then for each entry in the data set, find its deviation from the mean. Then square each of these deviations. Then sum all these square deviations together, and then divide that by n to find the population variance, and take the square root of the population variance to find the population standard deviation. Okay. And so here's the example that I have, and I just want to show you how I would work through this myself. So I have these 10 numbers together, and remember that we found the mean to be 41.5. So first I write down all these numbers, so the 10 numbers in the column. Then I form this column of deviations. I look at each entry and look at how far it is from the mean of the data set. So 41 minus 41.5, negative 0.5. And then I add, and then I do that for every single entry. Now, if I just add up these deviations together, they're always summing to zero. So I want to turn these negative numbers into positive numbers. So I square the deviations up. Okay. So if I square the deviation, so that's negative 0.5 square, which is 0.25. And then I square all these numbers up. And this is where I get the sum of squares. Now that I have the sum of squares and I know that n is equal to 10, I can calculate the population variance, which is the sum of square deviations, which is 88.5, which is what I calculated as the sum of this column, divide by n, which is 10, which gives me 8.9. And the standard deviation is just the square root of the variance. So the standard deviation is just the square root of There's 8.85, which is about 3. Okay. All right. One crucial thing to note here is like the difference between the formulas for when you're dealing for calculating the variance or standard deviation when you're dealing with the population data set versus a sample data set. If you're dealing with a sample data set, so if you want to calculate the sample variance when the data is not about the entirety of the population but only a subset of that population, then the entire process stays the same, but instead of dividing by n, we divide by n minus 1. Okay. So if I'm calculating a sample variance, remember that I'm always going to divide by n minus 1. So the sample standard deviations is the square root of the sample variance. Okay. So this is very important. There is a argument here called the degrees of freedom argument, which makes this formula come true, which is beyond the scope of an introductory class in statistics. But you have to make sure that you remember that there's this difference in formula between when you're calculating the population standard deviation, when the data set you have is about the population, versus when you have the data set as of a sample. If it's a sample, divide by n minus 1. If it's a population, you can divide by n. But otherwise, the recipe stays the same, right? If you're dealing with sample data set, we find first the mean of the sample data set. So you add up all the entries and divide by n, and that's represented by x bar. Then you take each entry and subtract the mean, find the deviation from the sample mean, square those deviations from the sample mean, find the sum of squares, find the sum of those square deviations. And because it's a sample data set, now you divide by n minus 1 to find the sample variance as square. And then the square root of the sample variance tells me the sample standard deviation. Okay. So to see this in action, here's a similar example. So the starting salaries are for the Chicago branches of a corporation. So instead of having the starting salaries of everyone in the corporation, we have only starting salaries of the Chicago branch of this corporation, which straight away tells you that what kind of data set is this? This is a sample data set. I don't have information on the starting salaries of everyone who works in a corporation, which is what would constitute the population data set. All I have here is the starting salaries of all the people who work at the Chicago branches of this corporation. So I know that this is a sample data set. Okay. So now that given that I know that this is a sample data set, I know that I have to calculate the sample variance and the sample standard deviation, and I know the formula is different slightly. Okay. But the basic mechanics are still the same. So first I calculate the mean. So I add up these 10 numbers, divide by 10. That tells me that it is 41.5. Then I take the deviation of each of these numbers from the mean. So that's all the same. Then I do the square deviations. That's all the same. So the sum of square deviations is 88.5. The difference comes here. So when I go to calculate the sample variance, instead of dividing that 88.5 by 10, which is what I was doing in the case when the data set was of the population, in this case now I divide by n minus 1, which is 10 minus 1, which is 9. Right? So this turns out that the sample variance here is 9.8, and then the sample standard deviation is just the square root of the sample variance, which is 3.1. Okay? So when we are trying to find a measure of variation to see how much variability there is in the data set, there is two crucial insights to remember. One is that we are going to measure variation relative to the mean, right? So once we find the mean, the first thing we do is find the average, the mean, which tells me what the typical entry in the data set is. Then I want to know how the rest of the data set, all the other entries in the data set are distributed in relation to the typical entry, which is the mean. And that is where this notion of this deviation from the mean comes from, right? Now there's a difference in the formula between when we calculate the variance in the population versus when we calculate the variance in a sample data set. Right? If we're dealing with sample data, then we divide by n minus 1. So the basic process still stays the same. We take each entry, subtract it from the mean, square it, add all those numbers up, and if it's a population, then divide by n. If it's a sample, then divide by n minus 1 to find the variances. And the standard deviation is always just going to be the square root of the variance. All right? All right. So what does this standard deviation tell me? What kind of information does this standard deviation tell me? Okay. So the standard deviation tells me what is the measure. It's a measure of the typical amount an entry deviates from the mean. So here's the first. Let's look at these three examples that I have here. Here's a data set where all five entries are just fives. Right? So I have eight entries. Sorry, there's eight entries. So frequency is eight, and all eight entries are just fives. So it's just five, 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 eight times. So what is the average of those eight numbers? So I add up eight times and divide by eight. The average is five. What is the standard deviation? How much variation is there in this data set relative to the mean? There is no variation because every single entry in the data set is the same exact entry. What variation is there? There's no variation. And if you calculate the sample variance here, that's going to be zero. So sample variance of zero indicates that there is no variation in the data set, but all the entries in the data set are identical. They're exactly the same entry. And that's what a sample standard deviation or standard deviation of zero indicates. Here's a second case where, the sample mean is at 5. So the average is at 5 and the standard deviation is 1.2, right? So that's fine. Okay, so this is a distribution where the average, the typical entry is 5 and it has a standard deviation of 1.2 units. Okay, and here's a data set where the average is the same as this one, 5, but you can see that it's not like all clustered together in this nice fashion here, but they're all like far apart. And because they're far apart, the standard deviation is going to be larger. So a larger standard deviation indicates that there is more variability in the data set. A smaller standard deviation indicates that there's relatively less variability in the data set relative to the mean of the data set, relative to the average in the data set. Okay. All right. Which takes us into a couple of uh, good rules that you need to know, right? The first thing is what we call the empirical rule, right? The empirical rule tells me that if I have a just a sec. Okay, so the empirical rule gives us a rule of thumb for very specific distributions, right? So if we have data that we know follows a symmetric bell-shaped distribution, so I'll show you the shape. So if we know that the data follows a distribution like this, is what we call a symmetric bell-shaped distribution, because it's symmetric in the sense that if I draw a line through the center of the data set, it's going to break into two equal mirror images. They're going to look like mirror images of each other and they're symmetric. So if I have a bell-shaped symmetric distribution like this, what the empirical rule tells me, this is just from observation, that about 68% of the data, so given that this is where the center of the data is, this is where the mean is, about, so if you start from the center of this distribution, which is where the mean is at, uh, if you take one standard deviation steps to the left or to the right of the mean, within this one standard deviation band between the left and right of the mean, the empirical rule tells me that 68% of the data set is inside this band, right? So 68% is within one standard deviation, which is to say 34% is in the left half and 34% is in the right half because it's symmetric, right? They're equal. Similarly, if I take two standard deviation steps away from the mean on either side, so starting from the mean, if I go two standard deviation steps to the left or two standard deviation steps to the right, then about 95% of all data should be within those two standard deviations. And then within three standard deviations, about 99.7% of all data set is in that region. Okay. So an empirical rule is a very the rule of thumb, more or less, where it tells us, if I have a symmetric bell-shaped distribution, that about 68% of the data set lies within one standard deviation of the mean, 95% of the data is between two standard deviations of the mean, and 99.7% of the data is between three standard deviations of the mean. Okay. So if you want to see how we apply this in general, so here's an example of how to use the empirical rule. So a survey was conducted and the sample mean height of women in the United States was 64.3 inches. which is a sample standard deviation of 2.62, right? So we know this is the data that the average height, the average in the sample of women that we collected was 64.3 inches, and the standard deviation that we saw observed inside the sample was 2.62 inches. We want to estimate the percent of women whose heights are between 59.06 inches and 64.3. Okay? So suppose this distribution is bell-shaped. Suppose I give you that information, then and symmetric, then this is what the distribution looks like. At the mean, the mean is now 64.3, right? So I want to know what percentage of women are between 59.06 and 64.3. 59.06, if I look at it, right, if the mean is 64.3, it's two standard deviations to the left of the mean, right? So it's from here to here, right? Because if I look at it, the 64.3 is here, that's where the mean is at, and 59.06 is here. Yeah. So between 59.06 and 64.3, what percentage of women do I expect to be in that height range? Now, from my empirical rule, from the symmetric distribution that I have, I can straight away see that 13.5% plus 34, which is that 47.5% of women are between 59.06 and 64.3 inches tall. Okay, so how do I come up with this? 59.06 is just 64.03, 64.3 minus 2 times 2.62, right? So that's what tells me that this is two standard deviation steps to the left, and this is just the mean. So I want to know what percentage of the distribution is between these two ranges, and I can calculate it this way. In a more general case, there's what we call Chebyshev's theorem. So if we don't have a symmetric distribution, but we have any kind of general distribution, it doesn't have to be symmetric. It can be any general distribution, doesn't have to be well-shaped, it doesn't have to be symmetric. Chebyshev's theorem puts like a lower bound on how much of the data should be in each of these ranges. And what Chebyshev's theorem tells me is that between k standard deviations of the mean, at least 1 minus 1 over k square of the percentage of the data should be in that range. So what does it mean? So if I have any random data set where I don't know whether it's bell-shaped or symmetric or anything, there's no any constraints on what it can be. Chebyshev's theorem tells me that within two standard deviation steps of that mean, about 1 minus 1 over 2 squared, so that's 3 over 4, or at least 75% of the data is going to be within two standard deviations. Within three standard deviations, going to be 1 minus 1 over 3 square, which is 1 minus 1 over 9, 8 over 9, which tells me that 88.9% of the data, at least 88.9% of the data is going to be within three standard deviations of the mean. It can be more than that. It can always be more than that, but it can't ever be less than. Okay? So for instance, if this is the distribution that I'm working with, I know that the mean is 39.2 and the standard deviation is 24.2, 24.8. And this is for population data. That's why mu and sigma here. And you can see that this is some general distribution, right? It's not uh, it's not bell-shaped, it's not symmetric, it doesn't follow any of the rules that we wanted to follow for us to apply the empirical rule, but we can still say that, with Chebyshev's theorem, what can you conclude? We can conclude that within two standard deviations of the mean, right? If I go to the left, 39.2 is somewhere there, let's say. If I go two standard deviations to the left or two standard deviations to the right, I should observe at least 75% of the data set, right? So two standard deviations steps to the left of the mean is 39.2 minus 2 times 24.8. So that's negative 10.4. And two standard deviations to the right is 39.2 plus 2 times 24.8, which is 88.8. It tells me that at least 75% of the population of Florida is going to be between 0 and 88.8 years old. Okay. All right. So Chebyshev's theorem, unlike the empirical rule, is just going to tell me at least what percentage of the data should be in each of these ranges that I've described. Right? It's not telling me precisely what percentage of the data is in any of those ranges. It's just telling me approximately what percentage of the data, at least the minimum, floor, the minimum percentage of the data which will be in any of these bands. Right? All right. So there's a couple of special cases that I want to quickly cover. When we have group data, how do we calculate sample standard deviation? And then we have a second special case which we call a coefficient of variation. Okay. Okay. So here's the story. So suppose you collect a random sample on the number of children in each household, right? And so you collect this data, and so you go to these 50 households, and then you collect how many children they have, the data on how many children they have. And you can see straight away that I have these 50 households, and there's going to be a lot of repetition in this data, right? Like most households will have one, two, or no children, and that's going to be a lot of repetitions of zeros, ones, and twos inside my data set, right? So instead of just doing like, calculating this deviation for each of these entries over and over again, I can just group the data together, right? So instead of like just finding the average and then doing the deviation and the square deviation and then summing all of that over and over again, I can just group the data together, and that's what I've done in this case, right? So I know that there is 10 zeros in the data, so I've just made a nice little frequency distribution. So there's 10 zeros in the data, there's 19 ones in the data, there's 7 twos in the data, 7 threes in the data set, and so on and so forth, right? So from this, I can straight away, first of all, calculate the average for the entirety of the data set. So there's 10 zeros in the data set, so that's 0 times 10, which is 0. There's 1 times 19, so there's 19 ones, so I'm adding 1 19 times, so that's 19. I'm adding 2 7 times, that's 14. I'm adding 3 7 times, that's 21. So I'm adding all of that up and dividing by the total number of entries in the data set, so that's 91 over 50 or 1.8, right? So the sample mean is about 1.8 children who are in the data set. So now I can go ahead and calculate the deviation, right? So a household which has no children deviates from the mean by 0 minus 1.8 or negative 1.8, right? Is lower than the mean by negative 1.8. So that's the deviation. Then I square the deviation. So I square negative 1.8 square, which is 3.24. And then how many of these numbers do I have? I have 10 of these. So I multiply that by 10, right? So instead of doing the same calculation, if I wrote this down without grouping the data together, then I've performed the same calculation over and over and over again. And in this case, I save myself a lot of time and effort by just doing the calculation one time and then multiplying it by the appropriate frequency, right? So for instance, households which report that they have only one child, right? So they deviate from the mean by negative 0.8. Their square deviation is the square of that deviation, which is 0.64. And there's 19 of these households in my data set. So I'll just multiply that by 19. Right? So this is a quicker way of just getting to the sum of squares very quickly. So 145.4, this tells me the sum of squares. Because it's a sample data set, now I divide by n minus 1. And so the standard deviation is just the square root of the variance. So that's the sum of squares over the n minus 1. So it's about 1.7. So standard deviation in this case is about 1.7 children. Okay. So sometimes, it's useful to consider whether the data can be grouped. If you can put it inside a frequency distribution, and if it's a reasonable thing to do, then you can really simplify this calculations, right? So otherwise you could just do it mechanically, right? There's 50 entries, so each entry I would do 1 minus 1.8, then minus 0.8 squared, and then do that calculation. Then again the next entry is 1, again I have to do the same calculation. So instead of doing all of that, I can just use a frequency distribution and then run the math much more easily and quickly this way, because I see a lot of repetition in the data set. That gives me an idea that I can group this data together inside a frequency distribution and leverage that to calculate these variances and standard deviations. Okay. Okay. So the last thing I want to talk about in this section around variation is this what we call coefficient of variation, right? Now, this is a good way of being able to compare two different kinds of things, right? So the point is that, okay, so the coefficient of variation tells me as a fraction of the mean, so if it's a population data set, the mean is mu, what is the ratio of the standard deviation in that data set to the mean in that data set times 100%. So it's reported as a percentage. So it's just telling me this fraction, this ratio between the standard deviation and the mean in the data set. So if it's a population data set, it's sigma over mu times 100%. If it's a population, if it's a sample data set, then it's going to be s over x bar times 100%. So it's just telling me what is the ratio between the standard deviation and the mean. Okay. Why would we need something like that? Because it lets us compare things which have different units. For instance, uh, here I have data on the heights and weights of a basketball team. Right. Now imagine that the heights are measured in inches, the weights are measured in pounds. Right. So now this is uh, this is a player whose height is 72 inches and the weights here are in pounds, right? So if I have a question to say, okay, is there more variation, right? Is there more variation in the heights of basketball players, or is there more variation in their weights, right? So how do I go about this? And to make this kind of comparison when the units are different, I could use what we call the coefficient of variation, right? Particularly when the units are different. Otherwise, also it just makes comparison between different kinds of variables easy, right? So if I think about the coefficient of variation, the mean height, so if I calculate the mean here, I've calculated the mean, the average height is 72.8 and the standard deviation is 3.3. So the coefficient of variation of the height is the standard deviation, which is 3.3 over the mean, which is 72.8 times 100%. So I can see that it is 4.5%. Similarly, I can calculate this for weight, right? The average weight is, if I calculate the average of this column of numbers, the average weight there is 187.8 pounds, and the standard deviation there is 17.7. So the coefficient of variation is 9.4%. So what this tells me is, as a proportion of the mean, the standard deviation is about 9.4% as a proportion of the mean. This essentially scales everything up by the mean of the variable that you're considering. So it allows us to compare things. So here, if I look at the coefficient of variation of weight as a percentage of the average weight, variation is about 9.4% versus the coefficient of variation in height. The average is 72.8 and the standard deviation is 3.3. So the coefficient of variation is here 4.5%. The higher this number is, the more variation there is, right? So here we can look at this and say that the weights here are more variable than the heights, right? So the coefficient of variation is just applying what we already know. We are looking at the typical entry and just expressing everything as a proportion of that magnitude of that mean, right? So we're looking at the ratio of the standard deviation to the mean, and then we can use that to compare. Because now, if you think about the units here, height is measured in inches, so it's inches here, so inches over inches, so it becomes units less, and then you can compare just the percentages. All right. So that's the last thing I want to talk about in this section around variation is what do we mean by measures of variation? First thing is that we want to know how much dispersion. Is all the data clustered together or is it far apart? So to think about this, the first intuitive measure we can come up with is to say, okay, let's look at where the minimum entry in the data set is. Let's look at where the max entry in the data set is, and let's look at the range of the data set, the difference between those. That's okay, but it's not like a very precise measure and doesn't tell us as much information as we need. So second order of thing is to think about, okay, we know what the typical entry in the data set is. We want to know how the rest of the data is distributed around this typical entry. Uh, So that's where this notion of a variance and standard deviation come around, and we looked at how do we calculate the standard deviation variance in a population versus a sample. Then we also looked at what happens, how we can apply this empirical rule when we have this bell-shaped symmetric distribution. We can use this empirical rule to estimate what percentage of the data is in any of these ranges. And then we use Chebyshev's theorem, which is a more general result, which tells us at least 1 minus 1 over k square percentage of the data is within k standard deviations of the mean, right? Then we talked about when we might want to use how, sometimes you might want to just group the data together and find the standard deviation and the variance that way. And then finally, we talked about how to use a coefficient of variation to compare variation in different data sets, right? All right. So last thing that I want to cover here is what we call measures of position. This is the end of descriptive statistics. We've come a long way. If you think about the road we've been on, we started with a raw data set. We began to sort that data set. Then we began to visualize that data set. Now that we have the visualization, we began to calculate some key summary statistics of it. We calculated typical entries, then we calculate measures of variation. And the final thing is that we want to know relatively what the measures of position are. Okay, so we'll talk about what we call quartiles and the box and whisker plot, and then we'll finally talk about a percentile and a z-score. Okay, so quartiles is a very simple idea. Fractiles is the general term of just saying that we break the data set up into different partitions, right? Fractals is, as the name suggests, are fractions. So it's about like describing the different positional elements of the data set. We say in this position, this is the entry, in this position, this is the entry, in this position, this is the entry. That gives us a flavor for what the distribution inside the data set looks like. A quartile, as the name suggests, essentially breaks the data set up into quarters, right? Into 4 equal parts. And straight away, intuitively, you can think about, if I have a long stick and I have to break it into 4 equal parts, what do? I first break that stick into 2 equal halves, right? And then I take each half and then break them into 2 equal halves. And that's it. And that's how I know what the quartiles are. So if I look at the where I should break that entire data set up into, I need to know 5 different entries, right? I need to know where the min entry is and where the max entry is, and I need to know where the breakpoints are, right? So the second quartile is where I break the entire data set into equal halves to begin with. We already know what that should be. That should be the median of the data set, because the median is the midpoint or the middle or the 50% entry of the data set. So Q2 is just going to be the median of the data set. Then I take each quartile, each half of that data set, and find the median of each of those halves, and then I have the quartiles. Okay, so here's an example which should make things clearer. So here's 15 different numbers. First, I sort them, put them in order. And now there's 15 numbers, which means that the median can be directly found, right? The median is the middle entry. So this is the middle entry, which is there's 1, 2, 3, 4. There's 7 entries to its left, 7 entries to its right. So this is the 8th entry is the middle entry of a n plus 1 over 2. So if there's 15 numbers, then the middle entry is the 8th entry here. And this is Q2. This is what we call quartile 2, right? The median of the data set. So now we've broken the entire data set into 2 equal halves, one which is called the lower half, one which is called the upper half. Now, in order to break these into halves, I need to find the median of the lower half, and I need to find the median of the upper half. So if I have to find the median of the lower half, then here it will be 10, right? And this is what we call quartile 1, because that is the middle entry of the lower half, because it's 6, 7, 8, and then 10, right? And that's the 11, 5, 15, 17. So that's the Q1. And then this is Q3. So if I look at the upper half, the middle entry of the upper half here, the entry which breaks the upper half into 2 equal halves is where this entry 31, right? So this is Q1, which is the first quartile, Q2, which is the median of the data set, Q3, which is the median of the upper half of that data set. Okay? So this gives us a sense of what positions at what different positions what the entries in the data set look like. Okay. So there's this notion of what we call the interquartile range. The interquartile range essentially tells me how far these two things are, where Q3 is and where Q1 is. The difference between these two numbers is what we call the IQR, or the interquartile range is just Q3 minus Q1. Okay. So in this case, we found Q1, Q2, Q3. Q1 is 10, Q2 is 18, and Q3 is 31. And then we can find the interquartile range is just Q3 minus Q1, which is 20. Okay. So we can represent all of this in a plot which is known as a box and whisker plot. And as the name suggests, it's a very straightforward plot, and you need 5 key numbers in order to plot this. You need to know what the minimum entry in the data set is. You need to know what the maximum entry in the data set is. Those you can just pick up from the data set. But then you also need to calculate the Q1, Q2, and Q3. You need to know where the first quartile is, what entry represents the first quartile, what entry represents the second quartile, and what entry represents the third quartile. And then you can put them together in this little thing called a box and whisker. So it's called a box and whisker because there's a box. The box is around the interquartile range. So essentially, I have like um, I have a number line where I represent Q1, Q2, Q3. I box the interquartile range. So I put a box around Q1 to Q3 that tells me where the middle 50% of the data set looks like. And then I draw whiskers from Q1 to the minimum entry and Q3 to the max entry. And so this is what we call a box and whisker. Right? So in our particular case, if I look at my data set here, the min entry is 6, so I know min. I know the max entry is 104, so I know where it ends. I know Q1 is 10, Q2 is 18, and Q3 is 31. And I can use this to basically make this graph, right? So min entry is at 6, the Q1 is at 10, Q2 is at 18, Q3 is at 31. The box goes around the interquartile range. The interquartile range is everything between Q1 and Q3. So you box that up, and the last whisker goes from Q3 to the max value, which is 104, and you can straight away see that this is what it is. Okay. Okay. So with a quartile, remember the idea is fairly straightforward. You first take the data set and break it into half. So first you find the median of the entire data set. In this case, because there's an odd number of entries, the median can be found directly from the data set. If you have an even number of entries, we've already discussed it. You take the middle 2 entries and find their average. Now then you have the data set has been broken into halves. There's a lower half and an upper half. And then you find the median of the lower half, and then you find the median of the upper half. And once you have the median of the lower half and the upper half, now you know all the quartiles, right? You know where Q1 is, where Q2 is, where Q3 is, and you know where the interquartile range ends up, and then you can make this plot, which we call the box and whisker plot. Okay. All right. So quartiles means dividing the data set into 4 equal parts. You can divide the data set into any number of equal parts that you want. So a decile is where you take the data set and divide it up into 10 equal parts. So, if you have to break something into 4 equal parts, you need 3 breaks, like Q1, Q2, Q3. The other one is automatically known. If you want to break up the data set into 10 equal parts, and we have these deciles, or you can have percentiles where you take the data set and and divide them up into 100 equal parts. So for instance, SAT scores, they usually reported as a percentile rank. So it takes the entire range of the scores and divides them up into these percentiles, right? Where there are 100 equal parts. So what test score represents a 62nd percentile? So here's the 62nd percentile. So I'll show you that. So this is a 62nd percentile. And so a score of 1500 or 1600. So a score of 1600 represents the 62nd percentile. So what does it mean to be in the 62nd percentile? It tells me that 62% of the data set of all the scores that I have are below this point, and 48% of all or 38% of all scores that I have in the data set are above this point. So it gives me a measure of position. It tells me, relatively speaking, where each of these scores are located. So it tells me along the data set that I have, where are different positions located. All right. The last thing that I want to talk about in this lecture, and is the last, it's a notion that will come back to again and over again when we get into inferential statistics, is to talk about what this notion of what we call a z-score. Okay? The z-score tells me, it takes each value, right? So if you want to know if a particular value is typical or atypical, the first thing you want to know is how far is it from the mean, right? So you take the value and you subtract it from the mean. So that tells you how far it is from the mean. You divide that by the standard deviation to tell you how many standard deviation steps away from the mean it is, right? Given that standard deviation tells you how much variation there is in the data set, now you know how many standard deviation steps away is this particular value away from the mean. If this is a large number, that suggests that this value x that you're considering is really far away from the typical entry in the data set. And if it's a small number, that tells us that it's really close to the data set. We'll get into the z-score over and over again when we talk about a z-test and all of that in inferential statistics. But this is uh, I'm just introducing it to you right now because we've just finished discussing how we calculate the means and standard deviation. So it's useful to see this in that context, right? So for instance, we can compare z-scores to figure out if one particular kind of phenomena is more atypical than something else, right? So for instance, here's an example, right? In 2009, when Heath Ledger played the Joker in the Dark Knight movie, he was nominated. He was only 29 years old when he was nominated for an Oscar for his role, for a Best Supporting Actor Oscar for his role in The Dark Knight. Right. Penelope Cruz also won the Oscar that year for the when she was 34 years old for her role in Vicky Cristina Barcelona. Okay. So then we looked at the historical averages, right? So we wanted to know whether, given the historically what has been happening, what is the average age at which people win and how much variation there is in it. So if you look at the historical average, the mean was about 49.5, and the standard deviation for the best supporting actor category was about 13.8, right? So the average winner of the best supporting actor was about 50 years old, and deviation. So there was enough deviation. So there's about 13.8. The measure of standard deviation is 13.8. Same thing we did for the best supporting actress category. So the average was about 39.9 with a standard deviation of 14. Yeah. Now let's calculate these z-scores. So for Heath Ledger, if you look at Heath Ledger's z-score, his value, his age was 29. The average for that category of best supporting actor is 49.5. So this is how far Heath Ledger is from uh, the average person, divided by the standard deviation. This is how much general dispersion there is, how much variation there is in that category. So this tells me that Heath Ledger is 1.49 standard deviations below the mean. Okay. Similarly, Penelope Cruz's number 34. She was 34 years old, and then the average best supporting actress is about 39.9, and the standard deviation is 14. So it tells us that Penelope Cruz was negative 0.42, so 0.42 standard deviation. She was lower. She was younger than the average person who won. That we can. Both of them are younger, but relative to uh, all his peers who won a Best Supporting Actor award, Heath Ledger's much, much, much younger than Penelope Cruz was relative to the typical value, right? So Z-score usually tells us whether a particular thing is typical or unusual or whatever. So Z-score, which is between -2 and 2, is generally considered a usual. It's not that bad. Anything between -3 and if anything over 2, right, is considered unusual. And if it's anything over 3 or -3, anything less than -3, z-score can be both positive or negative. So if the z-score is anything less than -3 or greater than +3, then it's considered to be very unusual. Okay? All right, so that basically concludes this section on descriptive statistics. So again, if there's any questions, just leave them in the comments below the video, send me a email, or see me in office. So This is where we'll finish up the intro portion of the course, where we just talked about starting with raw data. How do we begin to analyze it? How do we begin to organize it, visualize it, calculate a few key summary statistics like mean, standard deviation, measures of position, quartiles, and so on and so forth. And this is where the descriptive statistics portion of the course ends, right? So in the next session, we'll begin talking about probability theory. And once we have the building blocks of probability theory in place, then we can move on and talk about the inferential statistics. All right. All right. So thanks everyone for listening, and I'll see you in the next one. Bye bye.